To make the game of stickball truly accessible to people who are visually impaired, we can introduce a simple but very effective modification to the equipment. By carefully cutting open a standard wiffle ball and placing a metal ball inside and securing it back together, I created an audible game ball. So now, as the ball flies through the air, spins, or bounces, the bell inside of it rattles continuously. This allows players who are visually impaired to audibly track the ball and know exactly where the ball is or if it bounces on the floor. By relying on the sound of the bell echoing through the field, players can easily track its exact trajectory, distance, and speed by ear, allowing them to time their swing and make a perfect hit. This makes the game more accessible and allows people with varying abilities to still play. Now let's talk about how stickball would be affected if it was played in microgravity on the moon or macrogravity on Jupiter. Let's start with talking about the moon. So the force of gravity on the moon is 1.62 meters per second squared, which is about 1/6 of Earth's. Because gravity is much weaker, both the player and the ball will move very differently, and it will completely change the game. One of the biggest changes will be the projectile motion of the ball. In stickball, players often throw long passes or launch the ball high into the air. On the moon, gravity would pull downwards on the ball much less strongly, so the ball would stay in the air longer, travel further across the field, and move in much larger arcs before landing. This would make long-distance passing easier and would force defenders to react differently because the ball would fall much more slowly. They could change the game a little bit by increasing the size of the field or even adding more players because the ball is able to move so much further. The first important equation is gravitational force equals mass times gravitational field strength. In microgravity, the value of g becomes much smaller. Since g decreases, the overall gravitational force also decreases. This means players and the ball would weigh less on the moon, even though their masses will stay the same. Because players weigh less, they could jump much higher and stay in the air longer while trying to catch the ball. Another important equation is force equals mass times acceleration. Even in microgravity, a player's mass does not change. Because mass stays constant, their inertia also stays constant. This means once the player starts moving, they would still resist slowing down or change in direction. Stopping would actually become harder because reduced gravity also reduces friction between the players and the ground. With less traction, players could slide further, overshoot turns, and struggle with fast cuts or quick changes in direction during the gameplay, which in traditional stickball is super important. Momentum would also affect movement differently. Momentum equals mass times velocity is an equation that I use when doing my calculations. So since the mass stays the same in microgravity, players can still build large amounts of momentum while running. Combined with reduced friction, this means players will continue moving for longer distances before slowing down. The ball would also bounce differently on the moon. Because gravity is weaker, the ball would bounce higher and continue bouncing for longer before returning to the ground. The moon also has almost no atmosphere, meaning there's very little air resistance, and without the air resistance slowing the ball down, passes and shots could travel much further than they would on Earth. Next, let's talk about how Jupiter would be affected and how playing on Jupiter would be different. So, the gravitational field strength on Jupiter is 24.8 meters per second squared, compared to Earth's 9.8 meters per second squared, so the gravity, as you can see, is much stronger. Both the players and the ball move very differently, completely changing the game. One of the biggest changes would be the projectile motion of the ball. In stickball, players often throw long passes across the field, and on Jupiter, due to the strong gravitational pull, it would pull the ball downwards much faster, causing passes to travel shorter distances and fall to the ground way more quickly. The ball would move in lower, shorter arcs, making long-distance passes more difficult. The game would have to be adjusted by making the field much, much smaller so that you don't need those super long passes. The first important equation is gravitational force equals mass times gravitational field strength. On Jupiter, the value g becomes a lot larger, so since that g value increases, the overall gravitational force also increases, meaning players and the ball would weigh more on Jupiter even though their mass is still the same. Because players would weigh more, movement would become more physically demanding. Running would require more effort, jumping would be harder, and players would not be able to stay airborne for very long. The sport would be a lot slower and be more focused on strength rather than their actual jumping ability. Another important equation is force equals mass times acceleration. So since the players have the same mass, they still have the same inertia. However, because their bodies weigh more, every movement would require greater force to accelerate. Players would feel heavier and less agile while running or changing direction. Stronger gravity would also increase friction between the players and the ground. With more force pressing players into the surface, they would have more traction while running. This means stopping suddenly or changing directions could become easier compared to in microgravity conditions or even on Earth, which would be very beneficial to the game. Another equation that I used is momentum equals mass times velocity. So since the players would likely have slower movement under Jupiter's strong gravity, their velocity would decrease, reducing overall momentum during gameplay. However, collisions could become more dangerous because players and equipment would weigh much more, increasing impact forces during tackles or falls. So another addition you could make to the game is that you don't allow tackling anymore because it would become a lot more dangerous on Jupiter if two players are colliding into each other. The ball would also interact differently with the ground. Stronger gravity would pull the ball downward more forcefully, causing it to hit the ground harder and bounce less. Those airborne plays would become a lot more shorter, and the game would likely stay closer to the ground overall. To see a clear difference between Earth's gravitational field and Jupiter's, I'm going to be talking about their escape speed and comparing the two. So, using the conservation of energy formula, I was able to calculate the Earth's escape speed and Jupiter's. Earth's was 1.12 times 10 to the power of 4 meters per second, while Jupiter's is 5.95 times 10 to the power of 4 meters per second. As you can see, Jupiter's escape speed is more than 5 times greater than Earth's. This comes down to the relationship between mass and radius in the formula. So, escape speed is directly proportional to the square root of the planet's mass. Jupiter has a mass of 1.9 times 10 to the power of 27 kilograms, making it 300 times more massive than Earth. Even though Jupiter has a much larger radius, which places an object on the surface further from the center of core gravity, its massive quantity of matter completely overpowers the distance factor. Because of this immense mass, Jupiter exerts a much stronger gravitational grip on objects, requiring significantly more kinetic energy for the stickball ball to break free and escape. To really understand the massive difference in gravitational pull between these two planets, let's look at the speed needed to get the ball to a height of 1 times 10 to the power of 5 meters per second, using the conservation of energy equation, where the final kinetic energy at the peak height is equal to 0. When I did my calculations, I found that Earth's launch speed to get to this height would be 1.39 times 10 to the power of 3 meters per second, and I found that Jupiter's would be 2.23 times 10 to the power of 3 meters per second. Even though the stickball is being thrown at the exact same altitude on both planets, Jupiter requires a much higher initial speed. This is because Jupiter's massive gravity accelerates the ball downward much faster than Earth's gravity does. To overcome that intense downward pull and reach a height of 100 kilometers, the ball needs a significantly higher amount of initial kinetic energy to begin than it would on Earth. To really see how the difference in gravitational pull between Jupiter and Earth directly impacts gameplay, we can look at what happens when you throw a stickball upwards with the exact same initial vertical velocity of 0.616 meters per second from a starting height of 1.42 meters using a kinematic formula. So my calculations show a drastic difference in the max height the ball can achieve on Earth versus Jupiter. On Earth, the max height it could achieve was 1.61 meters, and on Jupiter, 1.43 meters. On Earth, the weak gravity allows the ball to climb a noticeable distance before stopping and falling back down. On Jupiter, however, the intense gravity cancels out the ball's upward momentum almost instantly. The stickball barely leaves your hand before being pulled back down, which shows exactly why high arching passes and plays are completely impossible on Jupiter's macrogravity, and the game would have to be adjusted. Let's look at the potential difference needed between two plates to get the ball to the same height on Earth. At the top, I listed all of my initial givens. So I knew my mass was 0.03 kilograms already. I have a charge of 1 times 10 to the power of negative 7 coulombs, and an initial velocity of 0.616 meters per second, which I got from my maximum height calculations. First, I found the kinetic energy of the mechanical throw using the equation EK is equal to 1/2 mv squared. Plugging in our values, I was able to find out that the EK was equal to 0.00569 joules. Next, to find the potential difference between two parallel plates, to supply this exact amount of energy, I used the formula delta V equals EK over Q. Substituting our kinetic energy and dividing it by the ball's charge, gives us 5.69 times 10 to the power of 4 joules per coulomb. As you can see in my conclusion at the bottom, the joules per coulomb is equal to volts. So this means that the potential difference of 5.69 times 10 to the power of 4 volts is required across the plates on Earth to achieve the same vertical. For my next calculation, I wanted to find the potential difference needed between two plates to get the ball to the same max height on Jupiter as on Earth. So on the left there, I established all of my constants. So a charge of 1.0 times 10 to the -7 coulombs, a mass of 0.03 kilograms, and Jupiter's gravity, which is 24.79 meters per second squared. Subtracting the height on Earth versus the height on Jupiter, I was able to find the extra height needed, which was 0.01168 meters. To find the extra work required to overcome this gravity, I used the equation W is equal to mass times Ag times delta D. And when I plugged in all of my variables, I found that this amount of energy needed was 0.0086 joules. To find the voltage required to deliver this energy, I isolated for voltage using the formula W over Q equals V. Dividing our work yields to 8.68 times 10 to the power of -4 joules per coulomb. As I said in the bottom, this means a potential difference of 8.69 times 10 to the power of volts is required on Jupiter to supply the extra 0.0087 joules of energy needed to reach our baseline height.